Good afternoon, everyone. I really wish I could be there with you in person today, but I'm so excited to share our work with you virtually. My name is Mahmoud Kassem, and I'm a senior undergraduate student at NYU Abu Dhabi. Today, I will be talking about how we automatically generate labeled datasets of semantic code errors. This research is joint work with Francisco Ribeiro and Sarah Nadi at the Senate Lab. Right, so let me start with why any of this matters. APR, which is automated program repair, is the idea of having a tool fix bugs in your code automatically. Look at this example on the left. The function is supposed to subtract the discount from the price, but whoever wrote it used a plus sign instead. And that's a bug. An APR tool, a good one, takes this buggy version and produces the fixed version you see on the right. With that one test now passing. Simple idea, right? But to build and evaluate a tool that does this reliably, especially those that are AI based, you need thousands of these buggy fixed pairs to train and evaluate on. That's the key dependency, and that's what this talk is about. So, where do people usually get these pairs today? The standard approach is mining version control history by looking at commits where developers fix the bug. Here is a real example from many stubs 4J dataset. The actual bug fix is just one character change, which is not equal to equals, but the exact same commit also includes an unrelated date formatting change. When a model trains on this, it can't tell which change was the real fix. So the core problems are bug types are unknown and the data is noisy because commits are tangled, and that's we set out to solve. So what would an ideal dataset look like? So we've mentioned the problem with the current methodology is that it's usually noisy with unknown bug type and language specific. So the ideal dataset is just the opposite of this. Exactly one known error per pair, explicitly labeled with its type and generated automatically at scale. That's our goal, a clean labeled dataset you can use to precisely evaluate whether an APR tool handles off by one errors, for example, differently from condition errors. Now, how do we actually build this? We were inspired by the LLM4Code paper by Frank Tipp. Normally, in mutation testing, you use fake bugs to figure out how good your tests are. We decided to flip that focus entirely. We use strong tests to validate our fake bugs. This lets us to use LLMs as a mutation generator to collect a massive dataset for program repair. As you see on the slide, our pipeline guarantees three things. First, it's clean by design, meaning there is only one error per snippet. Second, it's labeled by construction because we tell the model exactly which error to inject. And third, it's fully automated so it scales easily. For this study, we targeted 6 specific categories of semantic errors derived from the taxonomy by Wang and colleagues. As you see on the screen, these are all syntactically valid bugs that looks perfectly reasonable but are logically wrong. Instead of reading each box, you can see they represent very common developer mistakes ranging from simple off by one errors in loops to swapped variables or flipped arithmetic operators. These are exactly the kinds of bugs that are invisible to the linter but will fail your tests. To run this pipeline, we needed a solid foundation of correct code with test suites already attached. For input data, we use HumanEval and BigCodeBench hard, with both give us the three things we need to have in one package: a task description, a correct Python solution, and a test suite to validate against. Let us walk through this pipeline and how it works step by step. First, we gather our inputs, which are the correct code along with the task description and our target error type. We merge these into a structured prompt and feed it to GPT 4.1 to generate our mutated code. Then comes the crucial step, where we execute this generated code against the original test suite. This acts as our filter. If the code still passes the tests, it means that the model created an equivalent mutant, so we discard it. We only keep the code that actually failed the tests. Finally, we take a random sample of these failing cases and manually validate them to guarantee our labels are accurate. So here is what we produced, 1,217 code pairs in total. Each one a correct code snippet paired with a mutated version containing exactly one known semantic error. On the right, you can see the breakdown by source. Validation accuracy means 90% of the manually reviewed samples had the error correctly labeled for human eval and 75.7 for big code bench. The lower number for BigCodeBench actually makes sense. The tasks are significantly more complex, so it's harder for the LLM to inject a subtle semantic error without accidentally breaking the code structure entirely. And here is the breakdown of our 1,217 pairs. Off by one and variable errors were the easiest to generate, while condition errors were the hardest simply because many functions lack conditions to modify. So how can the community actually use this dataset? We see four main directions. First is error classification, which means training models to pinpoint the exact type of bug rather than just flagging that something is wrong. Second is program repair, where this data can help build and evaluate new automated repair tools. Third, we can study error correlations to see if specific types of tasks naturally lead to certain bugs. And finally, we can use this for LLM failure analysis to better understand exactly why models write incorrect code in the first place. So to wrap up, the problem we started with was that existing bug fix datasets are noisy and unlabeled, making it hard to evaluate APR tools precisely. Our solution was to use LLMs as controlled mutation tools. We inject exactly one known semantic error per sample, validated by an existing test suite, and the result is 1,217 labeled Python pairs across six error categories, publicly available at the GitHub link on the screen. Thank you so much for your time today, and I'm currently live to answer any of your questions.